5 pages, right? Certainly different teams have different requirements, but you know, if your teammate can actually consume this and start working on this module from what you left there, then you know that's sufficient. Different team is different. All right? So that is essentially when we come to implementation. Right? So starting next week, we are moving into the implementation stage, testing stage, and delivery stage. Right? We're going to look at all the classical approach of the high-level design, mainly as a backup just in case you have to work C programs, Fortran program, and even COBOL programs. Right? IBM still is recruiting COBOL programmers if you like them, like that kind of job. Right? Fortran programs still need to be maintained. Right? A lot of C programs need to be maintained as well, and or even implemented nowadays. I mean, if you are implementing modules for operating system, device drivers, IoT devices, you're still looking at programming in C programming languages. You may have some Java programming, JavaScript programming, like Node.js, things like that, but there are a lot of more C programming. Because, I mean, what is, you may say, so yeah, my Java program is fine. Actually, Java's virtual machine is written in C and C++. Right? So we have to look at some traditional approaches. All right. So other things we need to discuss little. I mean, we're going to spend about 10 minutes on this. There are some other things that may come to in handy. One thing is called activity diagram. All right. So this is showing. This is when you have parallel executions, concurrent execution in your program. Okay? For instance, one thing that could go on in your program is, what if there are two clients active at the same time trying to send a message? Can your program handle that? That essentially is an example of this. You may say, yeah, they are not going to talk to each other and everything, but eventually there will be an entanglement point. You have to store the data in the same place. You have to maintain a consistent picture of all the chats. You actually have to deal with coordinations. Activity diagram is for you to deal with coordinations when you actually allow things to go in parallel and eventually they have to synchronize somewhere. Okay? This is the crux of parallel programming, distributed programming, process communication, threading. That's not going to be covered here in our class, but you need to know that there is situation. Actually, more likely than not, you are going to work on concurrent programs in your real job, then sequential program, right? Your computer is incredibly concurrent. Internet is totally distributed system, concurrency everywhere, parallel computing everywhere, right? Threading everywhere, right? This is a good diagram for you to capture that kind of action. This is another example. You may have different things going on at the same time. Then whenever you separate into different computation, I mean, eventually you'll likely have to synchronize them together to form a consistent picture. Other kind of diagram like packages. This one you guys are probably familiar how you assemble a jar file together, including your component together and into something that can be deployed, right? Some of you use the Eclipse. If you want a plugin, you just go download that jar and drop into your Eclipse, and you got that functionality. Packages, how you package components, create a component package that can be delivered together. right? It can be source code together, it can compile code, executable images, library, and so forth. So this is source code. Deployment diagram. This is basically say what it goes where. This is actually relevant to your project as well, right? Suppose your server program should sit on a server, right? But in our case, your computer is both a server and also a client, right? So this laptop, okay, is running the server program and also running the client program at the same time, okay? So in terms of deployment diagram, you actually say, my client sit on client computer, my server sitting on the server, okay? But they actually may be the same computer as you'll probably have. Your computer basically serve two jobs. One is the server, the other is the client. Okay, so that's deployment. Who are going to use that system? Where that system is actually deployed. Okay, I mean in the real life, I mean your amazon.com app is deployed on your cell phone, and the real amazon.com facility is actually deployed on AWS. Right? If you just have your Amazon app, can you actually do anything meaningful? Just have the app. It's easy. Just turn off your network connection and try the app and see what's going to happen. Most of our apps are useless without that backroom server. Only some minimum programs like simple games, okay? Your Tetris, okay? Your poker. Those kind of things actually can work as an independent app on your cell phone without network connection. That's what you use when you are aboard on aircraft, right? There's no internet connection. But most programs, like yours, that's why we actually create the simplest client-server program, because that's actually majority of the application you're going to implement. Majority. All right. So we have talked about the use case diagram. Talked about so how we go from use case diagram and going. That's when our requirement stage, right? Then we move on to high-level design, basically identifying the components, also known as classes, in our system. Then we realize that we can come out with state chart to describe the high-level behavior of our system, right? In terms of things that happen triggered by the interface, state, event, and so forth. Interaction diagram, sequence diagram, collaboration diagram provides you a way for you to write down your idea of implementing your use cases with your class diagram. Basically, how your classes, object of your classes, together deliver the system functionality, which are described by your use cases. Right? Essentially, for your study this term, here you got enough information. Okay? You may say, oh, for my whole term, I'm actually studying 4 diagrams. Yes, you are studying. This is the notation we use so that we can basically make sure that everybody uses the same notation, so we can grade, we can communicate, we can teach. However, what you're really looking at is requirement, high-level design, and detailed design. Those diagrams only for the purpose of recording your idea. So you can share this idea with yourself in the future, right? Or share this idea with your teammates. Use cases, high-level design, detailed design. Once you come to detailed design, essentially we connect right to what you have learned on the 100 and 200 level. Okay? All the 300 level and 400 level, 500 level, 600 level classes you might take basically provide you syntactic sugar for many different things. Better designs. Instead of using your linked list, you use a real database, right? Instead of using a binary search tree, you may have much better searching tools. Okay, that is actually how to code, how to design operating system, how to design operating system module, how to write thread-based programs. Okay, these are the things that you learn from other classes to give you better capability to do larger and larger systems. But fundamentally, you need to figure out what are the set of features you need to implement, how your component implement these features, and assign responsibility to each class, each object. And all other classes are essentially provide you templates. Okay? You go learn templates. We are incredibly pattern matching based animal. We see things before, then we know what to do next. We are essentially using templates to match pattern matching, then decide what to do. The same thing happened here. If you have learned a system architecture before, you have learned a client-server architecture before, right now we are doing a chat app. If you do other kind of client-server architecture, you know how to do it. Okay? So that is essentially how you are going to progress into getting more things done with programming. All right. So that will be our quick review of UMLs, basically as a vehicle to serve, as our vehicle, to study requirement analysis design. Okay. The second half of our class will cover. Essentially, we'll talk about classical design. This is when you use a Fortran programming language, C program. This is the way you have to approach problems. Then we're going to look at implementation issues with a focus on testing. Okay, how you test your system. We have been talking about how you test your system here as well, starting with your unit testing. Set up your test before you code. For instance, you set up a test for which call into your function of level-based traversal. Set that up first. Then, first time you call this function, you run this test case, you fail, right? Because you haven't implemented that functionality yet. As you gradually implement a functionality, you get better and better. Boom! Eventually, you're doing the level traversal, tree level traversal. You implement a functionality, and you already have a test case in place. Later on, if you modify that traversal function, you can always run that test case as a regression test to make sure that you didn't mess up since you already get it right before. Okay? We'll talk more about testing later on. All right, so let's look at our quiz today. Here is a little bit. You can see that I'm still lingering on the tree data structure. Okay? In this case, given a binary tree, I would like you to find the lowest common ancestor of two given nodes in the tree. If I can give you the pointer to those two elements in some way, or just name, or just pointers, depending on how you hold your nodes, right? Then I should be able to find the lowest common ancestor of that two elements. So this is our binary tree. So 1, 2, 3, 4, 5. What is the lowest common ancestor of 4 and 5? Lowest common ancestor of 4 and 5. 2. What is the lowest common ancestor of 5 and 3? 1. Okay? So how about 4 and 6? 2. All right, here you go. You need a, so you have the, you know what I expect as a requirement. Requirement is done. This is called requirement done. Okay, now it's really into detailed implementation and coding and testing to get it right. So this is, I'm already setting up a test case for you. Right? Setting up a test case for you. You should code this test case first. Then you can go implement your code to make sure your code is correct. All right? I will leave you guys to finish this. I have a department meeting at 1:30. Somebody is visiting, so I have to go to that. Go ahead.
The design document is due next Thursday or Saturday.
Thursday.
Thursday.
Yep.
Okay. So we follow the instruction of the project.
Yeah.
Of the syllabus.
Yeah. Yeah. All right. I'll leave you guys to finish the quiz. This is exactly why we all have a requirement document, right? So I can hand this over to you guys, and you guys know what to implement. All right. I'll see you next time.